In this lecture, we're going to be talking about operations on functions with a focus on composition of functions. But before we get to composition, let's talk about the standard operations that we're familiar with numbers: addition, subtraction, multiplication, and division. There's a kind of, sort of concise way to write these notations. I've got them on this slide here. For example, if you know you want to add two functions, f of x and g of x, there's a slightly more compact way to write that. You can write f plus g, the sum of the names of the two functions, in the first set of parentheses, and then the input variable afterwards. So f plus g of x means f of x plus g of x. And we can do that with the other three standard operations as well. F minus g of x means f of x minus g of x. F g of x means f of x times g of x. It's implied multiplication here and implied multiplication here. And f over g of x means f of x over g of x, provided that g of x doesn't come out to 0. You can't divide by 0. There's no new math here, it's just a new notation. So for example, if f of x is x squared minus 4x plus 2 and g of x is 2x squared minus 6, then f plus g of 3 just means f of 3 plus g of 3. F of 3 is found by plugging 3 into the function f, so that would be 3 squared minus 4 times 3 plus 2. G of 3 would be found by plugging 3 into g, that's 2 times 3 squared minus 6. Now we can evaluate in each set of parentheses. This is 9 minus 12 plus 2, that's negative 1, plus this is 3 squared is 9 times 2 is 18, 18 minus 6 is 12, and negative 1 plus 12 is 11. We can do the same thing for an unspecified input x. So f plus g of x means f of x plus g of x, and now we're just expected to add the two functions together. So this is x squared minus 4x plus 2 plus 2x squared minus 6. And this is just collecting like terms. X squared plus 2x squared is 3x squared. The minus 4x has nobody to play with, so we just copy that down. And 2 plus negative 6 is negative 4. And we get 3x squared minus 4x minus 4. That's the sum of those two functions. We can actually now use this result to check our answer to the first one. F plus g of 3 now means plug 3 into this newly constructed function, and we should still get 11. Let's see. That's 3 times 3 squared minus 4 times 3 minus 4. That's 27 minus 12 minus 4. That's 15 minus 4, which is still 11. We get the same answer either way. Let's practice the other three operations. Same two functions. The next example is g minus f of x. Well, that's g of x minus f of x. G of x goes first, so 2x squared minus 6 minus x squared minus 4x plus 2. Be careful here to distribute the negative. That's 2x squared minus 6 minus x squared plus 4x minus 2. And we collect like terms, we get x squared plus 4x minus 8. Our answer is a new function. We're not expecting a numerical answer here because we don't have a specific input. The next example says fg of 0. So this is the product of f of 0 and g of 0. And we have two options for how to do this. One would be to find fg of x first and then plug 0 into the result. The second is to find f of 0 and g of 0 independently and then just multiply those two outputs together. Multiplying f of x times g of x is going to require us to do the multiplication between a trinomial and a binomial, and then we're going to plug 0 into that. I think it's going to be faster to just plug 0 into each function. F of 0 and g of 0 are very easy to evaluate. F of 0 would just be 0 squared minus 4 times 0 plus 2, which is just 2. G of 0 would be 2 times 0 squared minus 6, which is just negative 6. 2 times negative 6 is negative 12. If we had to find fg of 0 and fg of negative 2 and fg of 8 and a bunch of outputs of fg of x, then it might have been a good idea to find fg of x in general, so that we could just evaluate that at multiple inputs. But here, where all we had to do was plug in one number, and in particular that number was 0, it was easier to just evaluate f of 0 and g of 0. The next one is the quotient of f and g evaluated at 1. This just means f of 1 divided by g of 1. And so I'm just going to plug 1 into f of x, put that on top. That's 1 squared minus 4 times 1 plus 2. G of 1 on the bottom, plug 1 into g and put that in the denominator. 2 times 1 squared minus 6. So in the numerator we get 1 minus 4 plus 2, that's negative 1. And on the bottom we get negative 4. And those negatives cancel. We would usually write this answer as 1/4. So those four operations between functions are something that you can do with numbers. I don't think there's anything really complicated here. You just have to get used to the notation, what the notation means. The other operation we're going to talk about is something that you don't do with numbers. You just do this with functions. It's called composition. We're going to talk about composing functions. The composite function f circle g, you read this notation as circle. Please don't say fog. That doesn't say fog. F circle g. The composite function f circle g of two functions f and g is defined by f circle g of x equals f of g of x. We're going to make g of x, the second function, the input to the function f, the first function. You can look at this in two ways. If we have a specific input, you plug that input into g, then you take that result and you plug it into f. Or, zooming out a little bit and just thinking of it in general, you're taking the function g of x and plugging it into the function f. We've already done something like this for difference quotients where we're plugging a plus h or x plus h in for the input variable. Let's do a specific example. Let f of x equal 3x plus 1 and g of x equal x squared minus 5. Let's find f circle g of negative 4. What does that mean? That means f of g of negative 4. We're first going to plug negative 4 into the function g, then we're going to take that result and plug it into f. Well, that means we have to start by finding g of negative 4. And g of negative 4 is the output of the function g when the input is negative 4. So I'm going to replace the x variable with negative 4, and I'm going to evaluate that expression. Negative 4 squared is 16, 16 minus 5 is 11. So g of negative 4 is 11. That means f of g of negative 4 is just like f of 11, because g of negative 4 is equal to 11. We're first plugging negative 4 into the function g, then we're taking that result and plugging it into the function f. F of 11 is easy enough. That just means plug 11 into the function f. And 3 times 11 is 33 plus 1 is 34. So we've plugged negative 4 into the function g, then we took that result and plugged it into the function f. This is called composition of functions. Well, we can do that in general. We don't have to do it for a specific number. What does f circle g of x mean? Well, it means f of g of x. Here we don't have an input to plug in for g first, so we can't simplify the input to a number. We just have to plug the function g into the function f. So the way I like to explain this is to first write out the skeleton of f, the outer function. What does f do? It takes 3 times its input and then adds 1. And what do we want the input to be? Well, we're plugging in g of x. And what is g of x? G of x is x squared minus 5. So we're going to plug x squared minus 5 in for x in the function f. We're composing the functions together by plugging one function into the other function. Now we can simplify. This is 3x squared minus 15 plus 1, which is 3x squared minus 14. And now we have a general formula for what you'll get when you compose these functions for any input. If you take a specific value of x, this will tell you what you'll get when you plug that number into g first and then into f. For example, if I evaluate f circle g of negative 4, well, now that just means plugging negative 4 into this. So that's 3 times negative 4 squared minus 14. Negative 4 squared is 16. 3 times 16 is 48. That's 48 minus 14. which is 34, exactly what we got when we plugged -4 into G first and then plugged the result into F. We've now got a general formula for that composition. Just to make it clear, this last step wasn't part of the second problem. I was using our result to verify our answer to the first one. You can see you get the same answer either way, whether you first plug -4 into G and then plug that result into F, or find the general formula for F circle G and then plug -4 into that. Same answer either way. Before we move on to another problem, I'd like to address something that you might be wondering about. When would you ever have to do this? When do you compose functions? Well, in a sense, you've been doing this throughout all of algebra, because when you solve equations, you're essentially composing functions together. Like when you square both sides of an equation, you're putting the square root function that you've got on one side inside of the squaring function, so you're composing those functions. But we do this in everyday life too, like when you're converting between units. We're going to use this a little bit differently. We're not going to use it for conversions. Aside from the way we've been using it in the background when solving equations, we're going to use composition of functions to describe what we call inverse functions later on in this course. For now, we're just trying to get used to the concept in general with no specific application. So let's do some more examples. We're going to work with the same two functions, but we're going to compose them in the other order. So the next example says find G circle F of X. That means G of F of X. So we're composing the functions in the other order. If you've never done this before, I encourage you to use that skeleton layout. Take the outer function and write its skeleton. What does G do? It squares its input and then subtracts 5. And what is the input supposed to be? The input is supposed to be F of X. And what is F of X? Well, it's 3x plus 1. So I'm going to plug 3x plus 1 in for x in the function G. Now I simplify. That's a FOIL process there. 3x plus 1 squared means 3x plus 1 times 3x plus 1. That's 9x squared plus 6x plus 1. Then I subtract 5, and I get 9x squared plus 6x minus 4. And there's the composition of those functions. Now we need to find G circle F of 0. Well, we already know what G of F of X is. It's 9x squared plus 6x minus 4. So G circle F of 0 would be 9 times 0 squared plus 6 times 0 minus 4. And that's -4. But let's pretend for a minute that we didn't already have this composition here. How else could we find G circle F of 0? Well, G circle F of 0 means G of F of 0. So first we could find F of 0, and that's easy, we can do that mentally. F of 0 is 1. So this is just G of 1. And now I plug 1 into the function G, I get 1 squared minus 5, which really is -4. I get the same answer either way. It was kind of silly to do it the second way because we had already come up with the general formula, but this verifies that you get the same answer doing it either way. Notice, by the way, that G circle F of X and F circle G of X were different. Go back to the previous slide. F circle G of X was 3x squared minus 14. G circle F of X was 9x squared plus 6x minus 4. It is possible to get the same answer when you compose two functions in either order, but it isn't a guarantee. And in fact, if you were to make two functions up off the top of your head, most likely they would not compose to the same thing. It can happen, it doesn't always happen. Let's try some more, and on this slide we're going to focus on finding general formulas. I want you to get used to this skeleton idea. So in this example, f of x is the cubing function x cubed, and g of x is this weird fractional function x divided by x plus 1. The first example says find f circle g of x. I want you to try that on your own. F circle g of x means f of g of x. F is this function which takes its input and cubes it. And the input is supposed to be g of x. I guess I could write g of x cubed here, but I know what g of x is. It's x over x plus 1. Then when you cube a fraction, you cube the numerator and cube the denominator. And you can multiply out the denominator if you want, but that's not super important here. For those of you that care, that multiplies out to x cubed plus 3x squared plus 3x plus 1. But there's no advantage to doing that. Like, you cannot cancel those x cubes. Please don't cancel those. Those do not cancel. X cubed is not a factor of the denominator. G circle f of x will be different. See if you can find G circle f. G circle f of x means G of f of x. And G is this function which takes its input and divides it by its input plus 1. And what is the input? The input is f of x. So the numerator becomes x cubed, and the denominator becomes x cubed plus 1. And again, those do not cancel. Please don't cancel those. And you'll notice that those two results are different. You don't get the same thing. For my last example on this slide, I'm doing something a little weird, but I want you to know that you can do this. This says G circle G of x. Here we're composing a function with itself. G of x. Well, G is this function which takes its input and divides by its input plus 1. That's what G does. That's the skeleton. And the input is the function G. So in both the numerator and the denominator, I'm plugging in the function G. Notice it's doing the same thing we did in the previous example, except the function I'm plugging in is x over x plus 1, the function G. To simplify this, we can multiply everything by x plus 1. X plus 1, x plus 1. In the numerator, those x plus 1's cancel and we just get x. In the first term of the denominator, the exact same thing happens. In the second term of the denominator, we're taking 1 times x plus 1, which is x plus 1. This simplifies to x over 2x plus 1. You can compose a function with itself. There's no reason why you can't. In fact, one of the most famous unsolved math problems, it's been around for a long, long time, is about repeatedly composing a function with itself. If you want to become math famous or even rich, because people have put bounties on this problem, you could try to work on it. It's easy to understand, but it's very hard to prove. If you're curious about it, you can reach out to me and I'll tell you about it. You can work on it. We won't have much use for composing a function with itself in our class. We might see it a couple of times with logarithms, but outside of that, it won't happen very often. I want you guys to try these. I want you to find f of g of x and g of f of x. Now, f is this function that cubes its input and then subtracts 2. And the input is the function g, which is the cube root of x plus 2. When we cube this cube root, those undo each other, and we just get x plus 2, and then we subtract 2, and this comes out to x, which is an interesting result and something we're going to talk about later on in the class. Whatever you plug into this, you get right back out. G of f of x? Well, g is this function which takes the cube root of its input plus 2. And the input is the function f. So I'm going to plug f in for x in the function g. Well, now these 2's cancel, and I get the cube root of x cubed, and the cube root of x cubed is also x. So if you plug a number into f, and then plug that result into g, you get right back to where you started. These functions kind of undo each other. These are examples of what we call inverse functions, and this is what we're going to study later on in the course. You can kind of see that these functions undo each other. Whatever one does, the other one says, I'm going to do the opposite. Like, look at what f does. F starts by cubing, and then it subtracts 2. Well, g unravels all of that. G starts by adding 2, which undoes the subtraction of 2. And then it takes the cube root, which undoes the cubing step. It unravels the other function, and f unravels g. We call these inverse functions, and this is the real reason why we're studying composition, but that's a topic we're not going to tackle until later on in the course. I just wanted to give you a taste of it here. The last thing I want to do is talk about decomposing functions. This is another one of those topics that you future calculus students will have to be familiar with. We're going to start with a composition of functions, and we're going to try to find two functions that we compose to get the result. So this says, find two non-trivial functions f and g, such that f of g of x equal the binomial 3x plus 2 to the 7th power. I'll explain why I put in this part about being non-trivial in a moment, but first let's see if we can come up with two functions that we can compose to get 3x plus 2 raised to the 7th power. Well, what I see is an inner function, 3x plus 2, being plugged into a skeleton of x to the 7th. So there's this function x to the 7th, and into that we're plugging in 3x plus 2. That gives me an idea of how to come up with my functions f and g. G is the inner function that's being plugged in. So that's 3x plus 2. And what function am I plugging that into? Well, the function that raises its input to the 7th power. We're calling the input x, so f of x would be x to the 7th power. If you check this, you'll see that it works. If I compose f of g of x for my example, f is this function which raises its input to the 7th power, and the input is 3x plus 2. It works. The order matters. If I flip these around, I don't get the same thing. F has to be x to the 7th, and g has to be 3x plus 2 if I'm going to use these two functions. We call this a decomposition or composite function form. And you can always check your answer by composing your two pieces. Just make sure you do it in the right order. This is f of g of x. Let me erase my answer and explain why I put in that non-trivial part here. There's kind of a smart-ass answer that you can write for these. Two, in fact. Here's one of them. I'm going to let f of x be the entire function 3x plus 2 raised to the 7th power, and I'm going to let g of x be the identity function, g of x equals x. If I compose these, do I get the original function? Well, of course. F is this function which takes 3 times its input, adds 2, and then raises that to the 7th power, and g of x is just x, so it just puts an x in there. Of course, if I plug x in for x, I get the same function that I started with. That's not a true decomposition. We call that trivial. Trivial meaning obvious in this case. Of course that works. That's not a useful decomposition. That doesn't count. In my opinion, it's even more smart alecky to flip those around. Let f of x be the function which just spits out x, and let g of x be the entire function that I want to use. F of g of x would now be, well, plug this in for x, the entire thing gets replaced, and of course I get the right answer, but you're cheating when you do that. That's trivial. Again, our answer, the one that would be useful for calculus purposes, would be to let f of x be the function that raises its input to the 7th power, let g of x be 3x plus 2, and when you compose those, you get the original function 3x plus 2 to the 7th. Here's another example. Find two non-trivial functions f and g such that f of g of x equals 5 over the binomial x squared plus 1. There are actually two really good answers here. There's one that's better for calculus purposes, but we're not going to focus on that. I just want you to come up with a non-trivial decomposition. It depends on what you see. This is what I see. I see 5 over something. And what do I need that something to be to get the original function? Well, I want to plug in x squared plus 1. So to me, the inner function g of x is x squared plus 1, and the outer function is 5 over the input, which would be 5 over x, because we're calling this function f of x. If you compose these, you'll get the target function. F is this function 5 over the input. The input is g of x. G of x is x squared plus 1. It works. But you can look at this another way. There's another way to decompose this. You might see it as 5 over the input plus 1. And what would this input have to be? Well, we would just make that x squared. So g of x would be x squared, and f of x would be the function that does 5 over its input plus 1. If we compose these, we also get the right answer, the target function. This one isn't as good for calculus purposes, but again, I wouldn't expect you to know that, and it doesn't matter. So either of these would be okay. The only thing you really need to avoid for now is either letting f of x equal x or g of x equal x. Those would be trivial, because the other function would have to be the entire target function. I want you to try one on your own. Come up with a decomposition here. Find two non-trivial functions f and g such that f of g of x is the fourth root of the binomial x to the 8th plus 81. Here's what I see. I see an outer function of the fourth root of something, the fourth root of the input, and the function that I want to plug into that is x to the 8th plus 81. So I would make my inner function g of x, x to the 8th plus 81, And my outer function is the function that takes the fourth root of its input, and we're calling the input x, so it'd be the fourth root of x. That's what I would do. There's another reasonable answer, and that's to see the skeleton of the function as the fourth root of the input plus 81. And what would I have to plug into that? Well, x to the 8th. So you can make the inner function x to the 8th, and the outer function the fourth root of x plus 81, and when you plug x to the 8th in for x, you get the target function. That's not my preferred answer. I would do this, but both would be acceptable. I'm just looking to see if you can decompose them at all without cheating by using f of x equals x or g of x equals x. So there's a taste of composition. We also talked a little bit about the notation that we can use for the more arithmetic operations of addition, subtraction, multiplication, and division. If you have questions about any of this, don't be afraid to reach out to me. You can find me in an office hour or just send me a bunch of emails.